Okay, so momentum. Momentum is a vector quantity that reflects the amount of motion. The momentum vector is in the same direction as the velocity vector and equals the product of mass and velocity. Now, change in momentum, symbol delta means change in means final minus initial. By definition, that'll be the mass times the final velocity minus the mass times the initial velocity. Factoring out the constant mass, we get this. Dividing and multiplying by time doesn't change anything. The reason we do that is that this ratio is now the acceleration. Really, it's only the acceleration for the case where the acceleration is constant, but that covers the case of interest to us. So the constant acceleration equals this ratio, and the product of mass times acceleration is net force. So we've shown that the product of net force in time is the momentum change. This is known as the impulse momentum theorem. So impulse, which is the product of net force and time, equals the change in momentum, which equals the mass times the velocity change. That says F net for the net force. Okay, so that's the impulse momentum theorem. Really, it's just a reformulation of Newton's second law, so in and of itself, it's not especially useful. Its only significant use is in the collision problem. In collisions, if we have what's known as a closed system, that just means a system that's cut off from the outside world. And a good example of that is masses on a frictionless surface, because there will be a normal force from the surface and there will be a weight, but those will cancel each other out, and therefore the only forces are internal forces, the forces between the two objects, and those are always going to be governed by Newton's third law. So when these two things collide, there'll be an action force. Let's do this one. There'll be an action force, and there'll also be a reaction force, and those two will always be equal to each other in magnitude and just opposite in direction. So these two forces, we could say this is F1. It's going to be the opposite of F2. Now, strictly speaking, there should be a vector sign on top of those two. Now, if we multiply by the collision time, that preserves equality. And then we realize that the product in force and time is the impulse, or the momentum change. So we have that the momentum change for a collision in a closed system, which means one cut off from the outside world where there's no outside forces acting on it, or at least the outside forces are balanced, that because the forces are equal and opposite, the momentum changes are equal and opposite. What does it mean to say momentum change is equal and opposite? Well, it means that, say, if one object loses a certain amount of momentum, the other object has to gain exactly the same amount. Well, that means then that the total amount of momentum for the system will remain constant, so the total initial momentum will equal the total final. There's a couple of ways to write that. You can write mv1 at the beginning plus m2v at the beginning is mv1 at the end plus mv2 at the end, or you can say the sum of all the initial momentum equals the sum of all the final momentum. An example. Let's say we have a car. Let's draw a horizontal surface here. Here's our roadway. And let's say we have a car, and the car is 1,000 kilograms, and it's moving at 8 meters per second, and it runs into a stationary motorcycle. That's the before picture. After the picture, the motorcycle is moving at 5 meters per second, and we're asked how quickly is the car going? Well, if we assume no braking, then the only external forces would be normal force and gravity. they'd be balanced with each other. The internal forces are an action-reaction pair. Therefore, we would expect that the total initial momentum would equal the total final momentum, or if we write that out in more detail, m1v1, because that's momentum, plus m2v2, that's the total initial momentum. That'll equal m1v1 plus m2v2 at the end. So this is true because there's no net external force. So substituting in, mass is 1,000. Now this is really a vector relationship, so I need to pay attention to direction. So this velocity is in the positive direction. This one is at rest, so it has no momentum. At the end, this speed is an unknown, so I use the variable v, and the 800 kilogram motorcycle is going at 5 meters per second in the positive direction, because again, these are all vector quantities. All right, so solving, this is 8,000, this is 4,000, bring it over, you subtract, you get 4,000, and it'll be kilograms times meters per second. Then we're going to divide by 1,000 kilograms, and that gives us v. So we can see that the unknown speed v is 4 meters per second. Now that's the first thing we were asked for. The next thing we were asked for is how much kinetic energy was lost. So if we apply the work energy theorem, we would say, all right, at the beginning there's kinetic energy for the car. At the end, there's kinetic energy for the car and the bike. And these will not be the same because the collision forces do work and create thermal energy. So kinetic energy we calculate using 1/2 mv squared. And then we just found out that the final speed of the car is 4 meters per second. So let's see, what have we got? That's 64, that's 32,000, that's 8,000, so far 24,000. And then this is 10,000, so bringing it up, I think we lose 14,000 joules of mechanical energy, and this is just going to be transformed into thermal energy mostly, because collisions generate significant amounts of thermal energy. And there's also sound, and there's also irreversible processes like bending fenders and things like that. All right, so that's typical analysis of a one-dimensional momentum problem. We can also look at collisions in 2 dimensions, where we will say the sum of the initial x momentum equals the sum of the final x momentum. By the x direction, I'm referring just to the right on the screen, and the y direction will be straight up. So in the x direction, you can see we're going to have to do a component here. That's going to be 3 cosine 50 for the speed. So that's the horizontal speed. Initially, the 5 kilogram has no horizontal component of motion because it's moving in the y-axis direction. Similarly, after the collision, the 2 kilogram is moving in the y-axis direction, so it has no x momentum. And then the 5 kilogram will introduce an unknown. It's moving at a horizontal speed vx. So this has been reduced to a calculation. We can find the speed vx. We also apply, oops, that's initial. Let's clean that up. We also apply momentum conservation to the y components. So we'll say that the initial y momentum has to equal the final y momentum. So here we've got a y component of speed. That's going to be 3 sine 50. And the 5 kilogram, now remembering vector direction, the 5 kilograms moving in the negative y direction, so it's downwards 1 meter per second. Likewise, after the collision, it's downwards 1.5 meters per second down the page, and then 5 kilograms times the unknown speed Vy. Now that's been reduced to a calculation. We could find the speed Vy, and then after we've worked out Vx and Vy, we can find the unknown speed V just using the Pythagorean theorem. Now there is another way to solve two-dimensional oblique collisions. Here's another collision. This mass is going to come in and strike that one obliquely, and then they're going to fly apart like that. You can actually solve it using the whole vector and using a vector triangle approach. Because if we don't break things into components, then it should be that the sum of the initial momentum vectors equals the sum of the final momentum vectors. Now initially, momentum is mv. You have 2 kilograms going at 8 meters per second. That's 16 kilogram meters per second just to the right. So our initial momentum vector is just 16 this way. Okay? So that's the initial momentum. Now for our final momentum vectors, there's 2 of them. Here you've got mv, 2 times 6.7. You have 13.4 units of momentum at that 10-degree angle. So that kind of looks like that. And then you've got an unknown, which is 10 v units of momentum at some unknown heading. Now, the law of conservation of momentum says if we add these 2 vectors together, we have to get the original amount, which was 16. So that essentially just means that we have a triangle, right? So we're going to add the 13.4 at 10 degrees. We're going to add that to the 10v, and we have to get 16 horizontally, just like that. So this then becomes actually a triangle that we can solve using the cosine law. So it may have been a while since math 10, or math 9 even. So c squared's a squared plus b squared minus 2ab cosine c. So the unknown side is 10v all squared, or 100v squared. That's 13.4 squared plus 16 squared minus 2 times 13.4 times 16 times the cos of 10 degrees, and that's been reduced to a calculation. You can now find the unknown speed of v. So this works great as long as one of the objects is rest and you only have 3 vectors, because 3 vectors will always add together to give you a triangle, which you can then solve. Now a bit of collision vocabulary. There's 3 types of collisions. There are the so-called elastic collisions. This is where the objects bounce off. And there's no thermal energy created. Okay, so as I was saying there before I was interrupted, at elastic collision, the objects bounce off each other and there's no thermal energy produced in the collision. The other end of the spectrum down here is an inelastic collision, or completely inelastic. And in that collision, the objects stick together. And then there's significant thermal energy in that one. And then in between, there's just inelastic, which is sometimes called partly elastic. So here, they bounce off each other, but again, there's thermal energy that's created. There's a loss of kinetic energy. So elastic collisions conserve momentum and also conserve kinetic energy. The mechanical energy before and after the collision is the same. All collisions in a closed system, whether they're inelastic or not, conserve momentum. But only elastic collisions conserve mechanical energy. And the kinetic energy will be the same before and after. Now, later in class, we'll introduce a parameter known as the coefficient of restitution, and we'll see that the degree of elasticity is related to the coefficient of restitution. It's on a scale that ranges from that was nasty. It's on a scale that ranges from 0 up to 1. So this is a restitution of 0, and this is a restitution of 1, and everything is between those two extremes. Okay, now if a collision is elastic, then we have another relationship that applies to it. So here's a collision. We're told it's elastic, and we're asked to find the speeds after the collision. So first we apply momentum conservation. 6 times 5, 2 times negative 2 because it's going to the left. And then after this collision, we've got two unknowns, so the final momentum will be an expression, 6u plus 2v. Now this is 30 minus 4, that's 26, is 6u plus 2v. Bring the 6u over, divide through by 2, which isolates v. This gives us an expression that relates u and v. Can't be solved yet. We need another equation. That comes from energy. We're told that, here's the work energy theorem, we're told that it's elastic. That means that there's no loss of mechanical energy, and this term is 0. Now that's only true for elastic collisions. Now, the initial kinetic energy, 6 kilograms going at 5 meters per second, 2 kilograms going at 2 meters per second. After the collision, we'll have the 6 kilogram going at speed u, which is unknown, and the 2 kilogram going at speed v. So a half of 6 gives 3u squared, a half of 2 just gives v squared. So here's another relationship between u and v. Now where we have v, we'll substitute the above expression. So where we had v, we put in 13 minus 3u. So then you've got to square the bracket, expand using FOIL or the distributive law, bring the 79 over, gather like terms. These are all divisible by 6, so you get this expression. This can be factored, because 2 times 1 gives 2, minus 5, minus 3 gives plus 15, and then the cross terms, minus 10, minus 3, are negative 13. So that's 2u minus 3 times u minus 5. This first term, if we apply the 0 principle, 2u minus 3 is 0, so u is 3 over 2, second bracket is 5. The corresponding v values we substitute into this expression from the momentum law. We get 17 over 2, and negative 2. One of those answers, though, this one here, is to be rejected. Why? Because that's just the initial condition. So one way to conserve momentum and energy is just if nothing changes. So if we look back at the initial condition, we'll see 5 and negative 2 is what we started with. So clearly, ending with that would not be acceptable. So we're going to reject that solution. So this means this is the answer, this is the solution to our elastic collision. So elastic collisions, basically there's no such thing as an elastic collision. All collisions are inelastic to some extent. But if it does happen to be one of these imaginary elastic collisions, that gives us another equation that we can use.